Welcome back all. I hope you're all staying safe. This week, the lectures of this week, we are going to talk about rotation machine protection. We are going to do multiple of small lectures. Between each lectures, we will have a practical examples from the book. So far, we studied the protection of a transmission line, distance protections over current. We did differential protection for transformers, for a small transformers, how to determine the fuse characteristics. And then after this, we did a bus bar as well. Protections, we did a lot of example on the bus bar protection, similar to the three-phase transformer, single-phase transformer protection. Today, we are going to talk about rotation machine. What's a rotation machine? Rotation machine for us, it's going to be motor and generators. The protection. Now, what type of protections, what type of fault there is so I can design my protection system? Let's have a look. What type of protection do I have? What type of issues? Number one, I have inside the rotation machine, I have a windings. The windings could have a winding fault. So I could have a winding fault. This winding fault is related, could be related to single line to ground fault, for example. Winding to ground. So this could be winding to ground fault. I could have number two. For a generator or over motors, I could have some issues, speed issues or voltage issues. So let's put, for example, over voltage and then I could have also over speed. Over speed issue, and I could have now an abnormal voltage and frequency. I could have abnormal voltage and frequency. Remember when we did the electric machine? Remember the over speed, the over voltage? Now, in reality, I have to put some protections because this could cause major problem for me. And also frequency is very important. So now I have number four, abnormal voltage and frequency. I could have abnormal voltage and frequency. So now I have abnormal voltage and frequency. These are the common between rotation machines. Let's look specific at a couple of items for generator and for a motor that I'm interested in when it comes to my course material, to cover my course material. For a generator, as we studied before, I have to worry about multiple items. The interested items to me are under excitations and motoring stage. Remember the motoring stage and under excitation? So I go under excitation. So for a generator, I have under excitation, I have an under excitation, the second one is motoring and startup. Motoring and These are for a generator. Can you see this? Is that clear? So I have to consider, under generator, I need to consider under excitations, motoring stage, and startup. Remember when we did the electric machine, if I don't do proper excitations, under excitation could cause major problem for me, and if it goes under motoring and startup. For a motor, what do I consider for a motor? For a motor stage, I have to consider the stalling, the lock rotor, single phase, and loss of excitations. So this is for a generator. For a motor, I have to worry about something called stalling or rotor lock. You know, the motor, if you remember, the motor concept is when you have a three-phase, for example, motor, the magnetic fields rotate and forces the rotor to follow. If I have any problem issue, I could have it stalled. It's called stalling. So this could be I could have an issue for the single phase. And the last one is loss of excitation. These are the important element. Let's take a moment to recap. For rotation machine, my interest is regard to winding fault, could be winding to ground fault. I have over voltage, over speed, abnormal voltage and frequency. For the generators, I'm interested in two cases, under excitations and motoring and startup. For a motor, stalling, single phase, loss of excitations. Now, I want to start with my stator fault. What's a stator fault for me? Stator fault for me is for the windings. I have a windings. I want to consider a fault for the windings. Let's take a moment before we delete this to capture this information, and then we will start with a stator fault. I'll start with a stator fault. Now, whenever for a stator fault, I need to look for the generator. If I have a generator, pay attention to this. Generator bigger or equal to 1000 kVA, bigger or equal to 1000 kVA, or I have a motor bigger or equal to 1500 horsepower or greater, equal to 5 kilovolt in a voltage operations. Under this condition, differential protection will be used. Under this, I will use differential protection. Under this condition, I will use differential protection. Now, I'm talking about windings. I'm talking about the windings. Stator fault. Motor generators. Depending on the size, I will use the differential protection. Great. Now I want to highlight one element. If I'm designing a differential protection for the generator or motor. All my appliances for the CTs, the circuit breakers, the relay, everything located in a close proximity. This lowered the error. This lowered the burdens, the error. Remember, for the long lead. Also, so this will lower the errors. Also, I have one voltage. So what I do now is I can use the same CT characteristics. I'll use exactly the same CT characteristic because I have only one voltage, so the CT ratio type are the same with matching characteristics. Remember, let's look at this. I have a windings of, this is my winding of a transformer. I have this CT, I have this CT, the one voltage, everything the same. This characteristic of the CT exactly matching. So, which means also reduces my error. Now, I wanna make sure that you all follow this advice. The CTs will have the CTs must be dedicated and not used for any other application unless it's been studied properly that there is no side effect. Which means if these CTs are designed for differential, do not use it for metering or for any other requirement unless this is being designed and tested and verified. So I don't want you to say, if I have a CTs for differential protection on a motor or a generator, what I do, I can take the data out of it for metering purpose. This could lead to an error for the operation. And this could also have major effect on the CT performance. Now, this is my system. So pay attention to this. I have this goes down to this is my current. So look, what I want you now to pay attention to is this system. This current is going to be this current. Now, under internal fault, and I have an external fault. I have two scenarios. If I have an internal fault or I have an external fault. For an internal fault, I will see, if I want to call this I1, this I2. I want to see I1 on internal fault plus I2. Internal fault. External fault, I see I1 minus I2. I see I1 minus I2. That's why there will be a big difference. That's why I will be big difference when I come to protections. Is that clear? Let's do now one small example, then we will break and we will do an example from our book. The example that we will do after this one, after this example, will be example 7.3 from our book. Let's now do a quick example. We have a generator. 15.5 kilovolt, 125 MVA, 125 MVA. I have X (0.2 per unit, and I have a system. This is my system. This is my CT across the windings. Then on this side I have a transformer that goes down to my utility. I need to assess, give me a different color. I need to assess a fault in here and a fault in here. I need to assess fault in here and a fault in here. I need to design the CTs. Before I do anything, I need to determine this I, and the rated condition. I need to determine the line current under full load condition, rated condition, which is 125 MVA, 15.5 kilovolt. So I can determine my CT ratio first, and then I will determine the performance under internal fault and external fault. Okay, great. What will be the current? I line. I use my equation. I line. It's equal to S divided by √3 V line. I'm not interested now when it comes to the angles. Remember, I'm not interested when it comes to the angle now. So which is equal to 125 10 to the 6 divided by 1.73 multiplied by 15.5 10 to the 3. If you use the calculator, this will end up 4,656. 4,656 amp. Based on this current, I can use the CT ratio. So therefore, I have a CT ratio of 5,000 to 5. I use a CT ratio of 5,000 to 5. I can use 5,000 to 1. I can use 4,700, 4,700. Let's use 5,000 to 5. So step number 1. See, this step, we used it in transformer protection. We used it into bus bar protections. Use it in a single phase and a 3-phase transformer protection. So number 1 is to determine the CT ratio. I need to determine the line current magnitude. This is the line current magnitude. This is my CT. Great. This is my CT. Now, what will be under an internal fault? What's an internal fault at F1 current? I need to know. Let's say at F1 current I have a 23, this current in here, this current in here. I want to assume this current is 23,000 amp. This current also 23,000 amp. Case number one. I want to assess the internal fault. Case number 1, I want to assess the internal fault. Under internal fault, I have the CT output. I have the CT secondary current under fault is equal to 23,000 times 5 divided by 5,000, which is give you 23 amps. So if I have a 23,000 going into the CT as a primary current, the secondary current of the CT will be 23 amps. Under internal fault, only one CT will have a 23 amps as a secondary output. Only one CT. Under internal fault, as you can see, under internal fault, only one CT will have. Under external fault, the current in here goes through the winding to this. So one CT will have 23 amps under internal fault. If you add them together, it doesn't matter irrespective of the secondary one, of the secondary CT of the second one, doesn't matter because now under, what did we say? Under internal fault, I1 plus I2. Look, one of the I is 23 amps. It should be 0. I should be 0 under normal conditions, almost 0. Under an external fault, see this? The current, the 23,000 amp going through both CT. So both CTs will read. Let's put it into heat. Under internal fault, we have one CT has its secondary current equal to 23 amps. So you can see that under internal fault, the current inside the differential relay is I1 plus I2, so it's a bigger than 23 amps. That's a huge. When it comes to an external fault, both CT has secondary current of 23 amps. So therefore, I relay will be equal to I1 minus I2, which is almost 0. I want to highlight one element that in practice, under practical condition, even the two CTs have the same characteristic because there's a lot of other element in the vicinity. The secondary current will not be exactly the same. However, under external fault, you will minus them, so the current will be very low. That's how I know if it's an internal fault, external fault. Internal fault must trip, external fault, the other circuit breaker will trip. They will have a different mechanism for it. Is that clear? Is that clear? Can you see? We will follow the same concept. We will follow the same concept throughout this differential protection, which is used everywhere, as we saw. Single phase protection, single phase transformer, 3-phase transformer, bus bar, motor and generators when they be above certain limit. I can use it also for bus bar when you have inductor, capacitor bank. So when I have a high voltage filters, I use differential protection under many considerations, under many apparatus. Also, when I have a bus bar, we saw under extreme cases, under extra high voltage, we can use high impedance differential voltage relay, which is also the same concept. So as you can see in your exam, the calculation of my line current, the termination of my CT, the secondary of my CT output, that always a differentiation. When it's internal fault, external fault, what will happen? All this information. If you comprehend the first couple of classes of the differential protection, all the other lectures, it's just adding more information for different machinery apparatus. Is that clear? Now, take a 1 moment break, and I want you to open your book. And we need to solve question 7.3. I need you now to open your book so we can solve question 7.3 in your book. Okay, guys, let's take a break.